Hi, welcome. This will be an overview for Project 1 for aerodynamics. Today we'll be simulating fluid flow over a rotating and stationary cylinder using inviscid, laminar, and turbulent flows. We'll be using Ansys to simulate this, and we'll start it off into the workbench that we have here today. We'll be using fluid flow and fluid, just drag that in. And we'll have to start off by making the geometry of the cylinder as well as the domain that it's housed in. In order to start designing, what we're going to have to do is we'll select our geometry and choose a modeling software. We can either choose Space Claim or Design Modeler. I'm going to choose the Design Modeler because I'm more familiar with it, but Space Claim is perfectly fine as well. We're going to let that load and we'll jump into that in a second. Okay. We have now loaded into the Design Modeler. What we are going to do is create our cylinder as well as our domain in Design Modeler. As a run through, in the problem it states that the cylinder is 1 meter in diameter, and the domain, what we're going to do is to make it large enough, we'll do a 50 by 50 square with the cylinder centered within it. We're going to start by selecting the XY plane, hitting the Z axis to view it from the top down, and I will speed up from here, but I'll just be designing and dimensioning the cylinders. Alright, now that I have finished making the domain of a 50 by 50 and the cylinder of 1 meter diameter, what we're going to do is turn this into a two-dimensional surface so that we can start meshing. To do that, we are going to navigate to Modeling, over to Sketch, and go to Concepts, and we'll do Surface from Sketches. We can see that it's going to be applied to the Sketch 1, and we'll apply. Right, after hitting Generate, what we've seen now is we have a surface from the sketch and a hole where the cylinder is supposed to be. We'll now get into meshing. We are back in our Ansys workbench. We can see now that our geometry has a check mark and we are ready to start meshing. To get into meshing, we are just going to double tap. Alright, we are back in our meshing window. We're going to start our mesh by inserting different methods, as well as adding different details, as well as sizing, inflation, and different options that we can do to make a good mesh for our simulation. Okay, we are in our meshing window. This is where we're going to start the mesh for our simulation because every simulation needs a good mesh for good results. We are going to add a couple sizing factors as well as different methods and inflation. I'll time lapse through that, but I'll stop where I put in certain parameters. So let's get that started. All right, at first we did our method of our mesh, we inserted that. What we're going to do, we did the entire body as our geometry selection, and our method we're going to use today is triangles. We'll generate the mesh and we'll continue from here. All right, we decided our edge sizing. This is the edge of our cylinder, the small circle in the middle. We decided to use an element size of 0.005, and the behavior we set as hard. We'll hit generate and continue with the mesh. Okay, we are now in the inflation stage of the mesh. What we did is we selected our entire geometry here for the scope, and for our boundary, we used the edge of the cylinder. Our option, we used first layer thickness, and we used the first layer height of 0.02, as well as a max layers of 100 and a growth rate of 2.5. We'll generate from there and continue. All right, as we can see, we have a very fine mesh around the surface of the cylinder, which is what we absolutely need. The mesh out here is a little bit too coarse, so we're going to change that in the statistics, and we'll navigate there in just a minute. Okay, what we did here is we set our element size. Our element size was a little bit bigger on default, so we set it to 0.15 meters, and we'll generate that. All right, well, we've generated our mesh. We can see how much more fine it is with the 0.15 element sizes. When we get close to the sphere, we also see that we have that inflation value and the fine mesh around the cylinder itself. From here, we are ready to start the simulation, and we're going to jump into that soon. All right, we can see our mesh has become a lot more fine with the 0.15 element sizing, as well as our aforementioned mesh around the surface of the cylinder. We only have one more thing to do, and that's to define the boundary conditions. We're going to be defining the left as the velocity inlet and the right as the pressure outlet, as well as a symmetry value, and we'll define the cylinder wall as well. I'll run through that in just a moment. All right, we can see here that we have the velocity inlet, the pressure outlet, the symmetry, which is top and bottom, and the cylinder wall. We are now finished with meshing. We can start continuing into the setup for the simulation. We are back in the workbench. We can see that our mesh still needs to be generated. So we're going to go ahead and update that. And now we have the green check mark saying our setup is ready to go. Our setup is actually the Fluent program, and that's what we're going to get into. We're going to go ahead and double click that. And for this, we're going to use double precision, and at least for my machine, I can at least use 4 solver processes. This just makes it faster, but 1 is completely fine. So we have now entered the simulation side of Fluent. This is where we will set up our parameters to figure out all the variables that we want to see, as well as our pressure contours or streamlines, plotting our coefficient of pressure and velocity distribution on the cylinder surface, as well as the drag and lift coefficient. To do that, we will have to set up our calculation and our simulation based on the setup values on the left-hand side here. Since we're doing inviscid flow, we don't have to worry about too much of these variables. It starts off with pressure-based, absolute, steady, and planar. This is the default options, and we are going to keep that because of the nature of our flow. Next, we're going to go head into models, and this is where we choose what type of flow we are using. Obviously, for inviscid, we're going to select inviscid. In the later parts, we're going to use laminar, and for turbulent, we'll use the SPALART, Alamaras. Turbulent can be used on any of these as well, but that's what we'll be using just for ease. So select inviscid for our inviscid flow. Next, what we're going to do is check our materials. Materials will be the fluid that we are running in the simulation, which is air. For ease of simulation, we can see that the density is given as 1.225, which is standard for air. For ease, we're going to just set this to 1 and hit change and create. Once we have the air selected, we can then go to the cell zone conditions, the fluid, the surface body fluid. This is the fluid that is in this green region, which is obviously air, but it's good to double check. We see that it's air, as well as it is our density that we set. We can apply that and move forward. Now we can set up our boundary conditions. We can see when we named in the meshing that it already has automatically set up which conditions, but we still have to set a couple more parameters within them. We can see the inlet and the outlet, as well as our symmetry being set, and then our cylinder wall being in the middle. We'll navigate to boundary conditions. We'll double click that to see our different ones. We'll start with the velocity inlet. Give that a second to load. Our free stream velocity defined in the problem is 10 meters per second, and that's exactly what we're going to be putting in for our velocity magnitude. This will be applying velocity to the velocity inlet we see here on the left-hand side with the blue arrows. Hit apply, and that should save. Our symmetry should have nothing. Yep, we'll keep that. Pressure outlet, we'll keep our gauge pressure to 0. We don't want a difference across here. And all the regular default should be fine. Normal to boundary, total pressure, that should be fine. Our interior surface body should not give us an option, and then we have our cylinder wall. Since we are doing inviscid flow, the cylinder wall will show up with nothing. Later on, when we do our viscous flows, for laminar and turbulent, we'll get an option for the wall if it's moving or stationary, and that will help when we're doing our rotational cylinders as well. But for now, we don't need to deal with this constant. Next, we'll move on to reference values. The reference values here, we're going to compute from the velocity inlet, and we can see that it did change all of our values, especially here, our density. They're the ones we set at the velocity inlet originally. From there, we can move on to the methods that we're going to use in the solution part. For simplicity, we're going to use the scheme simple, and we are going to use the pressure function as presto. You can use different ones, but that's the one that I have decided to use in the simulation. To check, we're going to check our monitors for our iteration and residuals. We'll head into monitors, navigate to residual, and the default value should be fine, the 0.001, and that should be fine with what we're working with today. As we move on, we're going to go to initialization. We will continue to select the hybrid initialization, and we'll set a higher number of iterations. Instead of 10, we'll use 35, and we'll initialize, and we'll see that running in the console below. And from there, we are practically ready to start the calculation. We're going to go over to Run Calculation. And for this simulation, I've decided to use 1,000 iterations. That should be plenty enough for our inviscid flow to give us good results. From there, we'll hit Calculate. And we can see our residual graphs moving and our iterations counting down until our last one. I'll let this load, and we'll go into seeing our results after this. Okay, we finally got our calculation results. It completed through its iterations. So now we can start figuring out our velocity and static pressure contours, as well as our streamlines and various other plots that we need to do today. So I will navigate over to graphics and go hit contours. And we're going to start with pressure. We'll enable the contour lines, select the entire body, and we'll go ahead and hit display. And no surprise that we have high pressures at the leading and trailing edge of the cylinder, as well as low pressures at the top and bottom. The inverse of that would be our velocity profile. So what we'll do is we will do the velocity contour in the same way that we did the pressure. And we can see exactly the opposite, practically a dead zone at the leading and trailing edge, and almost 2 times the velocity, which is an ideal case for a stationary cylinder in inviscid flow. I'm going to go speed up, and I'll get to the next plots for pressure coefficient and velocity distribution. Okay, what we're going to do now is we're going to get our XY plots for our pressure coefficient as well as our velocity magnitude on the edge of the cylinder. So we're going to head over to XY plots, and we'll start with the y-axis being pressure, and we want to look for the pressure coefficient along the cylinder wall. We're going to go ahead and save and plot that. And it is normal to see that we have 1 as a maximum, and it heads all the way down to -3 as a minimum for our pressure coefficient of a stationary cylinder. To do the same thing with velocity, we will head over to velocity, see the magnitude, and plot. We can also plot along the edge of the cylinder the entirety by doing the curve length. We do seem to get an offset value, so here it is offset slightly. We fix that just by doing an iso grid, or an iso clip, sorry. And when we plot that, we start at the 0 point of the cylinder, or the leading edge. So we have a maximum of 2 times the inlet velocity, which is nominal, and back again to the pressure. We can see, sorry, the pressure coefficient. We can see it is 1 and -3. We're next going to move on to the streamlines, and then eventually the drag and lift coefficients. To get our streamlines for the stationary cylinder, what we're going to have to do is head back into our workbench and go ahead and hit results. And we're going to let that load up and switch you back into that. All right, we are now loaded into our results page. We can see our old mesh here. We'll go ahead and look at it on a 2D perspective. To insert the streamlines, we're going to go ahead and hit this icon for streamline. We'll just call it streamline 1, and we'll make sure it's a 2D or surface streamline. We shall choose our surface to be symmetry 1, and our number of points will be 400. We're going to go ahead and apply, and we'll load into that once it's ready. All right, now that we can see our streamlines have been generated, we have about 400 lines going across, as stated before, with our number of points. It matches up well with our velocity profile that we've seen earlier. We can now jump back into our previous window to see how to get the coefficient of lift and drag on this cylinder. Okay, we are back in our fluent window. We left off with the pressure coefficient graph. What we're going to do is calculate our lift and drag coefficients. To do that, we're going to go over to reports and go ahead and hit forces. In the X direction along the cylinder wall, we're going to be calculating our drag because our flow is in the X direction, and we'll switch this to Y1 and X0 to be the lift. We'll go ahead and print this, and we see in the console that our total is near 0, which is expected because we won't have any drag on a perfectly inviscid flow around a stationary cylinder. We'll go ahead and do the same thing for lift, setting the X to 0 and the Y to 1, which is perpendicular to the drag. We can see that our direction has changed and that we are also, again, close to 0 for this simulation. Now that we know how to get all of our contours, our pressure coefficient and velocity magnitude graphs, our coefficient of lift and drag, as well as our streamlines, we can now apply it to the other cases using viscous and turbulent flow, as well as the cylinder rotating for once. I'll just run through that quickly, only showing the necessary parameters since we've covered it before. All right, this will be for the second case with laminar flow. This will be the stationary cylinder first. We are in a new generated setup page, and we're going to just change a couple of things. First, we will change our model to laminar, and we will then head over to the materials because we need to change our fluid properties. In the problem, we were told to have 150,000 to be our Reynolds number. After going through air tables to get the closest value to that, we are going to use a density of 0.21324 and a viscosity of 1.4216 times 10 to the -5th. I'll run through the rest of these quickly since we've seen this before. If anything changes, I will show on the screen. Just a note here on our cylinder wall boundary condition, since this is a stationary cylinder at first, we're going to choose stationary wall. We'll be moving on to moving wall when we do the rotating cylinder next. Alrighty, the calculation has completed. We did go for a couple more iterations just to test something out, but 1,000 will give you pretty much the same answer that we have here. We're going to go in and just show the quick contours and streamlines and other plots that are pertinent to the example, and we're just going to run through it quickly. If anything changes, we'll quit the time lapse. Okay, so we see in this region that we have a large pressure difference on both sides. We have some drag with a large wake region. It's a lot more apparent in the velocity graph as well, which makes sense for a laminar flow and the stationary cylinder. We're just going to keep going. You'll see the same thing in the streamlines. All right, our streamlines have been generated just by going back through the results page in the workbench, and it lines up pretty much with what we've seen in the velocity plot. We'll go ahead in to see the coefficient of pressure and velocity graphs, as well as the lift and drag coefficients. Okay, we are in the pressure coefficient graph. This is along the direction vector. We can also do it along the curve length. Keep in mind that this graph is a bit skewed because we are starting automatically here for Ansys. We could correct it like we did earlier, but I'm going to keep it as is. Additionally, we're going to go check the velocity graph as well from the direction vector. You can see both is 0 because we have a no slip condition on the cylinder, thus the velocity would be 0 on the cylinder. We'll head into the pressure coefficient, or my bad, the lift and drag coefficient from here. We just head into reports, forces, and we can see on the cylinder wall that we do have a pretty heavy drag coefficient, almost 1, as well as switching to lift coefficient, we have a pretty minimal lift coefficient, which makes sense. From here, we're going to head into the rotational examples of both 20 radians per second and 40 radians per second, both in the clockwise direction. They'll change the graphs up a little bit. We'll just run through those quickly. All right, we've set up the second case, the second part of the second case for a rotating cylinder under laminar flow condition. The first one that we're going to do here is a clockwise of 20 radians per second. All we had to change originally is these boundary conditions, where we'll see our wall, which is our cylinder wall. We went from stationary to now we're moving, and we went to rotational motion and put a -20 because of the clockwise direction. Clockwise is negative and positive is counterclockwise. All the same iterations and uh, parameters. We're just going to hit calculate and we'll see the stuff soon. Now that we have our results for our rotating cylinder, I went ahead and pre-rendered all the contours and streamlines. I'm just going to show you very quickly what we have so far. So we can see that we have a low pressure on the top, or what can even be more telling is a higher velocity on the top. This would make sense. The cylinder is rotating clockwise, hence the higher velocity on the top and the lower or negated velocity on the bottom. We'll head into the streamlines where that will make pretty much the same connection. Again, we see the higher velocity on the top and the lower dead velocity on the bottom. We can run back into Fluent and see our plots that we've generated. The XY plots for the pressure coefficient along the direction vector, as well as along the curve length. I'll show that. You can see that we're getting dramatically different answers. For a normal cylinder, we've had 1 to -3, but we've obviously changed slightly. Going into the velocity contour, we're going to run into the same issue that we've had with the previous. Um, in viscous flows, we're just going to have a 0 velocity magnitude because we have the no slip condition. Finally, moving on to our lift and drag coefficients. Our drag coefficient along the cylinder wall can be seen to be 0.9, similar to the non-rotating viscous cylinder. And if we find the lift, we can see that that value has shot up significantly. We have a 3.6 in this location, which would make sense with the rotation of the cylinder and the low pressure zone up top. Next, we're just going to simulate the 40 radian per second cylinder. We should probably have the same results, just a bit more drastic. I'll come back with that. All right, we are in the last part of case 2. This is the cylinder that is rotating at 40 radians per second. We have a pressure contour already generated, as expected. Low pressure, very high, a good amount of low pressure on the top. If we switch that over to velocity, we can see that there are high velocities up top, much higher than our free stream. If we continue to the streamlines, we've already generated that. Again, following the velocity profile, higher velocities up top, nearly a dead zone at the bottom. We can go back in to our XY plots. We can see our pressure coefficient plot along the cylinder wall. We'll do direction vector first. We get a plot that looks like this, as well as if we go along the curve length. Again, remember the curve length is slightly off with the cylinder not starting at 0. We could have a correction factor, but it will be fine. When we look at this plot, we see that there is a large dip to the pressure coefficient of nearly -8. We can probably assume that that is the top of the cylinder where the velocity is much higher and the pressure is much lower. Finally, we can go into the velocity contours or distribution plot. Again, no slip condition. We are getting no velocity on the cylinder surface. Finally, we can look at our lift and drag coefficients. Again, x in the 1 gives us drag. We can see that it went down slightly or is comparable to our last example with the 20 radians per second spin. What is more interesting is if we look at the lift coefficient, how it has drastically shot up because of the cylinder spinning so much more, getting much more higher velocities, just thus generating more lift. We'll jump into the last example, which is case 3. It's the turbulent flow around a stationary cylinder, and I will just show you the parameters that it change from here. We are going to change the Reynolds number, but I'll get into that once we're into the simulation for the turbulent cylinder. Okay, we are in our turbulent example for the stationary cylinder. A couple of things that we've changed from previous examples. A big one is our viscous model. We are using the Spelart Almaras viscous model. We could use any of these, but that's the one I chose to use, except obviously for laminar and inviscid. And we also changed our air properties. We went with a density of this and a viscosity of that to achieve a Reynolds number of 800,000, which was included in the problem that we needed to solve. To make sure that everything was updated, we also went into the reference values and updated all of those for the velocity inlet. It should automatically update though. Other than that, all of our other parameters are the same mesh, same initialization, and the same amount of iterations that we will run. I'm going to hit calculate and generate all the plots like I did in previous examples. So here we go. Okay, we are in the turbulent cylinder example. We have the pressure contour rendered here finally. We can see a high pressure on the front end and dwindling back as we go towards the leading or trailing edge, excuse me. It's a bit more telling with the velocity contour. We can see a pretty defined wake region, but it's also pretty thin compared to our laminar flow case. Moving on to the streamline. Streamline again emulates the velocity case. We have that very thin wake region along with higher velocities at the forefront of the cylinder. Continuing back into the fluent, we can go and look at our XY plots, both for the pressure coefficient on the cylinder wall. Looking on our direction vector plot, this is what we see. If we want to look at the entire edge of the cylinder along the curved length, we can also look at that. We can see that we have a very varying plot, but we can also see that this is probably where these 2 points dropping is where we have those pressure drops or velocity increases along the cylinder wall. Continuing into the velocity profile along the cylinder wall. Again, no surprise here, we have the no slip condition, which gives us the zero velocity. We can then go into our coefficient of lift and drag. Again, x with the 1, that will be our drag. We can print that out and see that we have a moderately low drag compared to the other cases, 0.27. And with the lift, if we change these two numbers, swap them around, we can see that we have a very low lift, which would make sense. We don't have any spinning, and the flow is pretty even across the cylinder. This will conclude the tutorial with all 3 cases. We did the first case, which was a stationary cylinder under inviscid flow. We had case 2, which was separated into 3 different types. We had the all laminar flow, obviously. We had stationary, and then we had 2 rotatings of varying speed, both 20 clockwise and 40 clockwise. And finally, we finished off with case 3, which was the turbulent flow of a stationary cylinder. Again, we played with a couple density and viscosity values to achieve the Reynolds number that we wanted to do, but I feel like the animations speak for themselves, and that will conclude project 1.